let's start talking about some more advanced features. So something that you're going to run into very quickly if you start designing like real production smart contracts is inheritance. And often how this works is this, right? Just to motivate like why inheritance is a thing. If you're writing a token, you don't want to have to like write that token from scratch, right? You want to be able to reuse code. There's kind of two ways to do this. You could go copy someone else's code, right? You could go take, let's say we wrote a standard ERC20 and you could just go copy paste that and then now you edit it to do the things you want. This works, but it's just not very flexible. I guess it's flexible in the sense you can do whatever you want, right? But the right way to actually design software is to write the components that you care about and kind of like abstract away the things we don't. So, we actually provide a mechanism for this where someone could go write an ERC20 library and then we could go import that library and, use it ourselves. And as we're going to see here, only introduce new methods that we care about and perhaps even overwrite methods that something else has. So, we're going to write our library from scratch today, but, you could theoretically go download something like this. Just for simplicity in terms of package, having different crates and stuff, I'm just going to have the quote unquote library in another file. And we're just going to, import that module and, start using its methods and types and all of that. But, in the real world, what one might do is instead have a totally separate crate that instead of having a main.rs has a lib.rs, and you would go in that crate, declare all the things you cared about. So if we go together, here, you can see we currently have a main file. Let's go add another module. Maybe this module is called, I guess for lack of creativity, other.rs. So this is now another module. And in order to have this actually link against the rest of the program, or rather to let the compiler know that these are all part of the same thing, we're going to go add mod and then the file we made. So I made another file, so it's called other. And if we jump to it, we're going to see here that we're now in this file together. So now whatever I do here, I'm able to import and use here. So in other, I might similarly declare some storage, right? I might say that, hey, here's like some sub storage you care about. As before, I'm going to take the prelude and just import everything. But I might decide I'm going to create some Solidity storage. And in our case, we're going to have a structure named other. So we now have this module other linked in. And what we're going to do is actually, implement some additional things that we might expose. So to do that, I'm going to first import the stuff I care about from the SDK. In our case, I want some macros. So I'm going to do the prelude and then import all that. And then I'm going to just start using them just as before. So I'm going to write some Solidity storage. In our case, this will be some other thing. So I'm going to call it pub struct other. It might have some contents in it, right? It might be like we've got a flag and that flag is a bool. Or I guess since this is Solidity, we go the other way. So we got a flag, maybe we have a mapping. And it might have something maybe perhaps a little more useful than a flag, like maybe it maps addresses to uints, right? So this could be like balances. Of course, an actual library imported might have quite a few different fields, right? There might be quite a few different substructures. But what's kind of cool is, we'll just care about, all of this stuff's very general, right? So this simple example can be very clearly extended to other things. Okay, so we now have this structure, and it has various stuff on it, right? And it also implements Solidity storage, so we can actually go use it as a field in something else. Okay, so I've written this file. We're going to jump back into main, and I'm going to, import that thing from other. So, I'm going to say like I want that specific type from the other crate or module, and you're going to see here that it says it's unused, but that's okay. We're gonna use it. And I might actually go say after a bunch of different things here, like I don't know, maybe you have like a uint 256, which by the way is equivalent to just uint. And this could be like your total supply or all sorts of different things, right? You could define. Well, eventually you're going to say, I want an other. So this is that other structure from another file, this import. I am now able to use all of the stuff from other in the contract. It is a structure after all, right? So if in another method, right, I had, do something, and it took a mutable reference to state, and let's say it doesn't return anything, so we'll use what's called the unit type to just say, I don't return anything concrete that like you can go use. So at the end we'll just say, okay, return nothing. That's just some standard REST stuff, but I'm actually now able to do self dot, and then you're going to notice other dot, and then its field. So it had that balances, and balances is a map. So maybe I would go and insert something, or I would go and I'd remove something or replace or whatever, right? Depending on what it is, I might access different things and do stuff. So jumping back and forth between this balances here, you can see I'm referring to this thing right there. Okay, so that actually shows how you can connect the storage, but what we're actually going to do is inherit the methods of other. So that's where things get like really powerful. So far, all we really did was declare another structure that we could have just put in this file as well, and it had some state, right? But where things get like really fun is if we were to, jumping back into this balances here, what if we actually had a method that modified something, right? So similarly, I'm going to use external, and I'm going to implement some methods on other. And in my case, I'm going to say, maybe I have a method called getBalance, and what this method is going to do is it's going to return a U256. So U256 is just a 256-bit integer. It's what Ethereum uses. It's the same thing as this uint up here. Okay, so we're going to return that, and as before, we're going to just have a vector with the revert data, which we're not going to fill in our case. Okay, so because we actually want to access state and not have this just be pure, I'm going to say and self. And then I'm going to have this return the thing. So what I'll do is self.balances. And now with the map, you can do get, you can do various operations. I'm going to do get, and then we have to put in a key. Let's actually put in the person who called this contract. So in Solidity, that would be the message sender. So I'm going to once again import message, and I'm going to put sender. And what's really cool now is we're going to get the balance for this sender. And that's actually an option. So let's see here. We can, you're going to see that, of course, the types mismatch, but let's actually convert this into an option. And I just realized, right, in Solidity and in Rust here, there's no notion of like not having something in a map. Maps aren't iterable. They don't have, like a length. You can't like know how many items there are in the map. And so what we do whenever we can't find something is just return the 0 value for that type. So if I actually jump into get, you're going to notice that, well, I suppose the type definitions are a little complicated, explaining precisely what that does. But the long and short of it is we're going to get a value. And if I do this, we can actually check what that value is. You're going to see it actually is a uint. Now, that specific value could be the 0 value, but that's just kind of the trade-off that's made in the Solidity world. So we have it here as well. And since this is always successful, I'm just going to say, okay. And what that's going to do is, go query for the balance. If we've never inserted something, then of course it's going to be 0, but otherwise it's going to return whatever the specific caller of this contract has there. Okay, so that's get balance. And I guess we could theoretically have set balance, right? Now, if you were actually writing a contract, you probably wouldn't want to let the user be able to just set their balance freely. Perhaps you'd use something like, the message value and increment or whatever. In our case, we'll just be like really naive and simple and just say, for the message sender, I'm going to insert the value. Well, I guess in our case, it would be the call value. So I'm going to say message value, right? So in our case, that's going to insert. Now, insert doesn't return anything. So, we're able to just say, okay, we're done with that line and return success. And since, we're not actually returning anything meaningful, got to use mutability, we'll just return the unit type again. Okay, so now we have a get balance and a set balance. All right, now how do we actually link this together? Recall contract, which I'll put in another screen, right? Contract is the entry point. So right now, as written, when I call contract, we're going to look through the methods and see, like let's say I was looking for that get balance, right? I'm going to look through the methods and I'm going to say, okay, is this one it? No. Is this one it? No. Okay, I'm missing a method, so we're done. And that's all we specified. We have an entry point and it looks at this. How do we actually compose contract and other, right? Well, here's how we do it. We're going to use inheritance. Inheritance can mean a lot of things. It's different in different programming languages. We actually use something most similar to like Go, but the specifics of that aren't very important right now. What's really important is that we actually go and connect the things directly. So in our case, how this works is you write inherit, and this is this of course requires external. It wouldn't make sense to do it otherwise. So we're going to say inherit, and then we're going to say the name of the thing we want to inherit. So in our case, we're going to inherit the other type, right? Let's see the warning that we're getting. So I'm going to go over to the terminal, and I'm going to, I guess, just export the ABI. And we're going to see here that, borrow isn't implemented. So you could implement this yourself. You could implement both borrow and borrow mut, one after the other, for that. And I could be like impl borrow for contract. Well, what am I borrowing into? I'm borrowing other. And, you could implement this the standard way. You'd be like self.other. And then similarly, you could do the same thing for like borrow mut, right? I could say borrow mut for contract, and now I'm going to take mutable references. And you can see here that, let's make sure we got it. Borrow's not a member of trait borrow mut. Oh, right. It's actually called borrow mut, right? So you could just do this, right? And now all of a sudden you're going to see everything exports and works correctly. However, in order to make things nice so that you don't have to like write this every time, we've actually introduced a macro for you. So over in the definition of the storage, you're allowed to just write borrow. Now what that's going to do is just go ahead and implement borrow and borrow mut for this other type. And you can do this, by the way, for several different things. I could have some other type, I guess some other. And, I would be able now to go inherit both of those things. I could have my other, I could have my some other. These are not the best names, of course, but, you could add them. You can also choose, by the way, to put them in a list. I could have them one after another, or I could use commas and all of that to separate them. But the point is, I'm going to implement borrow. Now, importantly, I can only do this for one field of a given type. So I couldn't like impl borrow for two different ones, right? I couldn't have borrow other 2 and borrow other, because it's not going to know like which one you're wanting to borrow into. But that's kind of a quirk of the SDK. We're looking to get rid of this as we continue adding nice inheritance features and stuff. But currently that's how it works. Okay, now what happens? Well, if I export ABI, we're going to see something fascinating. Exporting this thing's ABI, you're going to notice, hey, there's Solidity inheritance, right? We have the contract and the other thing. So the other contract recall has this get balance, you can see it here, and the set balance, which you can see here. And we have those two methods, the purity and all that matches. You can see that, this one returned a U256, so we see a U256 here, etc. But what's really cool is this contract type actually extends that, right? And it introduces two new methods. Okay, now this behaves just like it does in Solidity. When you actually go call this contract, it's going to first look for a method among these two. And if it doesn't match, it'll then jump to the first thing it inherits and, take a look here. I know actually in Solidity it's kind of complicated how inheritance and which ones get checked first and all of that. And overrides, you don't need to know all about that stuff, but, in our case, this is just how it works, right? So in that same way I had other and then perhaps other things, it will check in that order. So it would first say, is it this method? Is it that method? And if it's not those things, then it'll go to other. And if it's not in other, it'll then go to the next thing. And then once it gets to the very last one, it sees, uh-oh, I didn't have a method, so I revert. And that just, fails. So that's actually how that works. And what's really powerful about this is it means we can compose these types together. If other was in some library, as you'll see in our ERC20 example, you can now go have all of its methods without having to bring that code in. I know we put it in this file, but conceivably, right, you would just go import some crate and it would be some standard, right? And you'd just be able to work on it. In terms of shadowing, if you want to do that, or overriding as it's called in Solidity, you can just go re-implement a particular method that you want to provide an alternative implementation for. So I might decide, you know what, I'm going to have a different get balance method, and the way it's going to work is it's just going to always be 0. Now, that would not be very useful, but the idea here is, let me make sure I am using the right one. Yeah, okay, so I've now imported U256. Now what this method does is it will, it'll return this, and it'll never actually get to this get balance. So if someone calls this contract, the invocation will find this function and return its result. It won't go over to here. This is very powerful, and it's actually very not Rust, right? Usually in Rust, we don't have this notion, but because we're designing smart contracts, a slightly different paradigm is pretty natural, and this is one way to do composition. What's super cool about the Rust SDK is you don't have to use it. You could just write pure Rust if you wanted, or C or C++, these other languages we also support. But the long and short of it is, this is just a way of composing different things together. And if you instead wanted to use more traditional composition techniques, you're totally able to, right? So if you're thinking of cool patterns or things that you could potentially write that people might use, well, how else might one decide to have some really cool or generic library that does a bunch of things? I'm being vague here, but you get the idea, right? The sky's the limit. You do whatever you want. It's not like Solidity where you have to do this, right? You can choose to design your contract however you like. Now, we've just provided some nice tools to get you started, right? We have all these different macros, and we actually have this thing that exports the interfaces, but it's up to you, right? You can design your contract, and in the same way in the same way you wouldn't be able to modify Solidity, or I guess in the opposite way, we're actually able to do that here. So you could go and instead of using our SDK, use someone else's or edit it to your liking. And we do accept PRs, so if you have any ideas, definitely let us know. Okay, so that's all that. We've done inheritance. We've looked at different storage and stuff. There's a lot of good things there. I think one last thing to look into is, or I guess actually before that, I'd like to talk about immutables. So notice right now we have these two different storage structs, but of course setting them requires actually calling something that sets them, and that requires an store. That's just EVM terminology for how we write stuff to persistent storage. And sometimes it's nice to just have something that's immutable, something that is just always true. Well, in Rust, we have a notion of immutability through constants. So you can either have a constant that you declare somewhere and you use it. I'm just going to assume that you kind of know Rust if you're doing this, but you can actually parameterize your storage types. So in the same way that you can parameterize a normal struct in Rust, recall you're able to add documentation and say a bunch of stuff. You're able to add various derived macros and stuff on top of this. You're able to do a lot of really cool things. Well, one of the things you're able to do is actually parameterize this other. Now, you want to parameterize it over something generally. So I might say I'm going to parameterize it over a t, and this t, I might put some bounds on. I might require that the t be, I don't know, clone, right, or something. And then you're actually able to use it in all of this stuff. So if the thing actually implemented Solidity storage, right, the storage type that is, then I could actually even perhaps put it here. I could say that this is a flag, that flag, which was a bool, is now parameterized by something else. And how we do this in Rust, right, everywhere that you have this, you're going to want to say that it's generic. And what's really cool, actually, let me say it's a storage type as well. You got to have the same bounds. And you can use where clauses and all of that stuff. But I put it in the wrong spot. So you're going to want to say over here, where t is the storage type, now I have that. And we haven't actually used other correctly right now, so I'm not able to, or actually, we'll just go ahead and make this program compile. So if I try to run it, you're gonna see we're gonna have an error because everywhere else we had other we didn't parameterize it accordingly. So I might now in my contract say, I'm gonna say that for our purposes, other is a storage pool, right? And now I've actually, put it on the wrong one. So in Rust, the type comes second, right? But in Solidity, I would do it like this. And so now, if I've gone through and parameterized it like this, this contract now works and uses this specific specialization of other. And I could theoretically, because these types are different, right, have some other T that I have this implement or whatever, right? And everything just works and is awesome. This is super powerful. Like there's so many things you can do when Rust provides generics for you, right? I can have my T here, I could have my T in the mapping, you can get crazy and like introduce other ones too and use where clauses, all that good stuff, right? Okay, for our purposes though, we're going to use it to give us the ability to do immutables. So that was like really cool that we're able to like have this stuff be so generic and general, right, is really the word I'm looking for. But how do we actually do, immutables or constants? Well, one way to do it, I kind of like this way, and you'll see it in our ERC20 example, is to define a trait over which other might be general. Or specialized on. So I'll declare a trait called like constants or something, if I can spell today. So I might say that this is my like params, right? These are like the parameters that configure your other. And I might say that it has a value called like, whether it's active, in Rust we use all caps. It's actually called screaming snake case, which is kind of fun. But you can name it like, we'll say active, and this is a bool. I do bools only because this is simple, right? In practice, you would have, other stuff. And maybe we decide to give it a default value, right? We might say that active is, a bool that starts out as false, or we might require that other people actually have to provide a value for it, right? But the idea is basically we're able to just have some various constants that we care about, right? So maybe there's like a length that this thing is generic over. You get the idea, right? Like there's just, the sky's the limit. You could have whatever constants you want in this trait. And conceivably you could even do functions and stuff, which allows for like, with some changes, you'd be able to do things like hooks and like in the ERC20 standard, well, it's not really standard, but you're just like able to add like transfer hooks. Stuff like this becomes possible through generics and stuff. So, we're constantly tweaking the SDK to make the stuff fully general, but you're going to notice here that we can now take advantage of this params on other. So there's kind of two ways to do this. You can either use your T somewhere in somewhere in your fields. Earlier we just decided that like the mapping had address to T or that the flag was a T. But in our case, we're going to just say, it might be the case that you don't use T. Like maybe T doesn't ever get used. Well, in order to solve this concern, a problem presents itself when you don't have T used anywhere, and it's just that the Rust compiler says that this is like too general, right? If we actually go and we run it, you're gonna see it says that this parameter is unused. This is just a requirement of Rust, and so how you deal with it typically in Rust is use this type called a phantom data. Phantom data is pretty involved, but it's kind of out of the scope of what we're doing today. You can import it. You can either get it from standard marker phantom data or core marker phantom data, depending on like if you want to build in no standard or not. But long story short, what this actually allows you to do is just say, hey, this T, I'm actually using it. Now, what actually is phantom for as far as we care? It's just a field that uses the T. It's of 0 size. It's not gonna like have like big performance problems or something. It doesn't change your storage layout. You could have other stuff after it and it's gonna be in the exact same slots as the phantom data, as if the phantom data wasn't there. But the point is we just use this T. Phantom data literally has an implementation of storage type that has 0 width. So you'll like actually notice that. And I could show you that, but I'll just let you go look in the docs for it. If you go jump to the storage folder and go to mod, you're going to see that in mod.rs there's an implementation for it, and it says that like this thing just has 0 size. It doesn't impact storage at all. But what it does give us is the ability to parameterize. Okay, so we're now making other generic over this phantom data. Now what I can do, which is pretty fun, if I say that for particular others that implement this trait params, I'm going to have like, special methods. Maybe I have a method that returns whether or not, I don't know, whether or not we're active. So, maybe this is actually going to be a pure method, which is kind of fun because it's not going to depend on state. Remember, this is something that's general. And we'll say that, it returns a bool. And what we'll literally do here is do pt, and then we're going to take our active constant, right? And what this just did is generate a pure method that returns the value that we made constant. And now, like, what values might you want to be constant? You might want the name of the contract or the number of decimals in your ERC20, right? Like the things that one doesn't want to have to compute or store somewhere, but that's always the same. Immutables are the solution, right? And yeah, that's basically the idea. So now if we go to the other file, we can make some changes, right? So instead of being general over, or being specialized by the storage bool, I might go implement the trait, right? So I might have a type called, like, I don't know, my params. And these parameters, it's just a type, but I'm going to actually go implement that trait for it. So I'm going to go impl params, which I need to, of course, import for my params. Oh, I need to say this is a struct. Sorry. So this struct is going to implement those things. So, I might say active in our case is true, and I might say that the length is 32. I don't know, or maybe 42. That's more fun. And then I'm going to just say that instead of having an other that's general over storage bool, which according to this does not have an external, I'm going to instead decide that this is going to be over my params. So this specific contract's definition for these params is what we're going to use. And similarly here, I need to make sure inheritance works. We're no longer inheriting from one that's specialized over storage bool. Instead, we're going to have my params be the thing. And I believe that should now compile. And you're going to notice, hey, here's that pure method active from earlier. Because it doesn't depend on state, we don't even have any args, right? We actually can return that value, and it can be all like super efficient and done at compile time, right? So that is how you do immutables. And this is just like so powerful and extensible, but yeah, I'll just let you go crazy with creativity with the stuff that you're going to build with this, right? So, okay, the last thing that would be worth looking at, like we could go over the whole SDK, right? We could talk about events, we could talk about, you get the idea. But I think what would be really fun in our case is to just talk about calling other contracts. So there's a few ways to do it, but this is just like the simplest way to do it. So from the top level type, if you just decide to import something, use this other macro called sol interface. And sol interface allows you to define interfaces. So I might have an interface for something, right? And of course, I would use, from the terminal, right? I would use this, this output to actually go get what I need, right? So, I don't know, maybe I want to be able to call let's see here, maybe I do want to be able to call get balance, right? So get balance, I'm going to go copy paste this. I can now actually go put this in my interface here. And I might name it, my other contract that I'm importing. I guess in our case it's called iOther, but that's like our contract, which is kind of weird. So we'll say dex. We'll say that the dex or something has this. I don't know. This is just a silly example that we have. And you just go copy paste that method. Now that we don't need other, I'm just going to drop that screen right there. So yeah, now we actually have imported get balance from that specific interface. And of course, you would just copy paste a big interface that you got from somewhere else, right? And now you're actually able to call the thing. So I could maybe in do something, go call get interface. And the way we might do that, well, I guess we actually need to know the address of the thing that we're calling, right? So suppose somebody passes you that address, right? So we'll say that, I don't know, this is the other contract, so I'll just call it contract. or maybe we'll call it dex, right? So that we're not like overloading these terms. So we'll say that the dex is an I, and you'll notice now we have this type defined IDEX. And IDEX is going to let us call dex, which is so cool. I can do dex dot, and you're going to notice it has a get balance method. It'll actually have every method that you care about here. Okay, so how calls work in the Stylus SDK is you have to provide a call context. The top level type is a call context, or rather, the top level type is one. So I can just use self. So this is and self, and I'm going to be able to call it. Now, it turns out that this method doesn't actually have any other fields to it, right? If we look, it doesn't have any other fields. And let's just see what error we're getting. So if I take a look at this, we're going to see here that this is important. So get balance is view. Okay, so I need a call context that, and we'll talk about what call contexts really are in a second. I'll need a call context that's view. Okay, so this call context self is mutable. So, I'm kind of using the wrong one. So I can just add an ampersand to say that I'm going to go call this. And you're going to see here that, actually I have to deref to do this. Okay. So this thing is mutable, but I want something that's immutable. To do this, we have a couple ways, but the easiest is to just deref and then take a reference to it. And basically what I'm saying is, no, I don't want a mutable reference. I want just the reference to it. And that allows us to, instead of having a contract that we're passing in, have an ampersand contract that we're passing in. Of course, if you were to instead try to execute this over in get owner, you could just use self, right? Because the ampersand matches up, or I guess you'd need the dex from somewhere, but you'd be able to use this one. I guess I'll just add it, IDEX. So you'll notice that in here I could use I can use and self. Here I have to actually explicitly be like, no, I don't want the mutable one, I want that one. Now, if instead of view, like let's say this thing was right or payable or whatever, I would just use one that was more appropriate for that. And let me make sure, I see that we have a warning. Let me just make sure we're good. So, we're fine. Oh, right. So right now, this macro is returning we're getting a warning because this is a interface that is camel case, and in Rust we use snake case. So you can actually, in all of these macros, whether it's sol interface or in the external one, you can always just write in snake case, and it will convert it to camel case. Like notice when I actually export the ABI, you'll notice that it's been turned into camel case. So when it comes to method selectors, just do it in the language's native way of writing things. Now what's going to be really cool soon is you're going to be able to overwrite it. You're going to be able to say, hey, actually, I don't want do underscore something to turn into do something. I want it to be some completely other method selector or something. We're going to give that ability soon, but right now it's just an automatic conversion. But okay, so that's why we had that warning. I'm really glad we looked at it because it's interesting. And so we now have the ability to go call that contract using various contexts. So we were able to use and self to do it, but how does a call context actually work? Well, this is just the simplest way to do it is you just pass a self, and that does a lot of great stuff and you're able to get your work done. But if you want to actually parameterize it, so you want to limit the amount of gas that you're sending, or you want to decide whether or not it's view or payable and how much value to actually pay, you can do this by creating a context, which you can import over in a context. So just to make sure you see the import here. So context lets us do something really cool. You start out by saying that this is just a new context. I'm just making a context, and this would be sufficient to call something that's pure or view. And actually, I realized that because this thing is view, that's all you need. But what you can do is then configure it. I could say, hey, I'm gonna set the amount of gas. So if I want to set the amount of gas, you're going to notice that on context, we have these different methods, and one of them is gas, another's value, and another is mutate. That lets you decide whether or not it's view or write or, something else. So I can say that I'm going to set the amount of gas, and the amount of gas I'm going to provide is, 32. And that actually has now limited the amount of gas that this gets to have. Of course, 32 gas is very, very little and will actually never succeed. So what you might instead decide to do is figure out how much, gas you have left and do some calculation with it. So what you can do is similar to a message. You can go import EVM, and then EVM will let you have gas left or ink left, which is another concept we'll maybe talk about later. And this is saying I'm going to pass all the gas that I have. Now, to be very clear, you don't have to say pass all my gas. It does that by default. And if you use a crazy high value, it'll just clip it to how much gas you have left. And the EVM has these rules for there's the so-called 64 over 63, or I'm sorry, 63 64ths rule, as well as stipends and all of this stuff. Stylus does all this for you. It's exactly like in the EVM, but the point is you just say how much gas you generally want, and it goes and does this for you. Now, generally we say it's kind of bad to have a hard-coded number. It's led to security issues in the past, but you get the idea. Now, that allows you to say how much gas you have. You can do other things though. You could say, hey, I don't want to just call this thing. I want to mutate this thing. I want to be able to call something that's not just view or peer, but write or payable. And you do this by just writing out, you do this by providing access to the top level storage. So in our case, self is the top level storage. I'm getting an error, of course, because, this takes a static call context that is something that's view, but I'm providing it something that's write. So I can actually just hack this a little bit and say, actually, this thing requires immutable reference. Write is the word we use when it's neither view, pure, or payable. In Solidity, you just don't write anything, and that just says I can mutate state at will. You'll notice that since I made that change, this is now failing, right? And it's because, I need a mutable reference, but the Rust type system isn't going to let me do that because this is a immutable reference, and I've now got I'm trying to get a mutable reference to it. So if that thing's going to be right, then I'm not going to be able to use that. Now, you might be thinking okay, isn't that kind of weird? In order to say that this thing's going to be mutable and do mutation, I have to pass in self. Why do I do this? Here's why. In Stylus, we implement really efficient storage caching. In fact, actually, the algorithm for it is optimal. So, in the EVM, you have to be really careful. In Solidity, you have to be really careful not to write to the same storage thing over and over or read to the same variable over and over. This is not true in Stylus. In Stylus, you're able to freely go and write to the same thing many times, read from the same thing many times. And it'll cost basically the same as doing it once. And the reason is we use a caching layer. You can turn this off, of course, but by default, the REST SDK actually provides caching. And this caching means that when you go do calls, we have to flush or clear the cache. You see, if I've got a bunch of stuff that hasn't actually been committed to state, I could have a problem, right? Which is that I could have stuff that's not yet committed, and then during reentrancy, that is where if this contract called another that then called back into itself, I would run into issues because, the values I was expecting to be at specific slots are not there yet, right? They're still in the cache. Reentrancy is disabled by default in Stylus, so most people don't have to care about this, but for logical and storage safety reasons, we have this, right? And so in order to make sure that it's never the case that a storage slot isn't correctly done, isn't correctly written back to disk and not just stuck in the cache or whatever, we require that when you call something mutably, you have to give it access to state. And this self, remember, is the top level storage object. So that means that using it, I'm able to if I have mutable access to it, I know for a fact that, if I go and clear the cache with it, I'm done, right? There's no possibility that some second reference or something exists and I'm going to read it afterwards and it's going to have a different value than what got written or what have you. So that's why we do that. You have to really think about this concept of aliasing, this concept of memory and storage unsafety to really think through that. But this is why you have to have that in order to mutate. Now, because we're in a method of the top level storage type, remember the one that's the entry point, you can just pass in self. If we were inside this one here, you're going to need to have access to the top level type. That's because having mutable access to part of the type, that's not the same as having it to the whole thing. And only this top level contract object defines the entirety of EVM state storage, right? Every storage slot that ever changes is under contract. So if I have mutable access to contract, I have mutable access to all of state. But if I only have some of it, I don't have that guarantee. And so it wouldn't be sound, as it's called, to do a reentrant call in here unless I had access to the top. Now, just for time, I won't go super into this, but if you wanted that, instead of making this and self or and mut self, what you would want to do is make this generic, and then generic over something that's a top level storage type. That's actually the name of the trait, and then have that as the first arg. And then you would actually be able to make calls and do all that stuff. And because you've implemented borrow, right, you could borrow into the thing you cared about. That's pretty advanced. It's like very, very pushing the edges of what inheritance is. And it is subject to change as we improve the code base. But 99% of the time, you don't need to really worry about that. But just I wanted to explain why this was here and, all that. Okay, and then lastly, I could actually decide like how much value to send. And then it would require that the method be payable, right? You're able to call other contracts using that, using those primitives. And you'll actually notice that these dexes here, these are actually just addresses in the exported ABI. So, right, like how do you actually say where the thing is? Well, you just pass an address to it. That's just how we decided to make this stuff generate. So that covers basically everything I wanted to. We've done storage, we've done methods, inheritance, we've done even calls and advanced calls where you're like parameterizing various things. So much is possible in what we've done here. So yeah, that's really fun. I hope that you'll be able to take this and go on and make amazing things. We have a hackathon or I should say, there is a hackathon in ETH New York that's coming up next month, or actually it's at the end of this month, and there's actually going to be $20,000 in prizes. So definitely go there. Maybe you'll be able to get an edge on the competition by having listened to this and learning more about how this stuff works. I will say, if you run into friction with this SDK, just realize that Stylus is an alpha, so lots is subject to change. If you run into issues, please open an issue on GitHub. Let us know. We have a Discord channel. If you actually go to the Discord channel in Arbitrum, there's one under developer called Stylus, and you can ask us questions and we can help you. I'm the Stylus tech lead, and I'm there all the time, and I love explaining this stuff and all that with people and seeing what they're working on. So if this stuff's exciting and fun for you, definitely go do those things. Go to the hackathon. And lastly, if you've made it to the end and you find this like really cool, you can actually get paid to do this all day long. If you come join us at Offchain Labs, we're looking for new Rust engineers. And so, if you're like really enthusiastic about programming languages and, Rust or really whatever, right? If you like these blockchain technologies, this might actually be really fun, right? You can just kind of like work on smart contracts and, what we're looking at together all day. So definitely apply. Look forward to seeing what everybody does, and GN.